So our presenters this evening are Angus Houston, Alex Quirk, Simon Crook, and Tim Wilson. Angus has 25 plus years experience in a career as a naval architect and structural engineer across naval shipbuilding, oil and gas, commercial sustainment, and mega yachts. He's done mainly structural design for both new builds and refits and sustainment projects. Angus worked in the UK until he came to Australia 6 years ago. Angus, I suppose on paper works for Houston Engineering, but maybe practically works for Altair. Alex Quirk is the next presenter. Alex has a master's degree in aerospace engineering. He started in Altair in the UK in product design consulting, doing design optimization for aero, automotive, and defense. From a maritime perspective, he worked on the Queen Elizabeth class carriers with BAE. He came to Australia in 2016 and now works as Altair's technical and sales manager for Australia and New Zealand across a range of industries. Simon Crook is the next one. So Simon works for Ship Constructor Software Incorporated. Simon has nearly 20 years of experience as a designer and CAD manager, spending most of that time working on refit projects for naval vessels in the Australian region. He started out working for AMT and has also spent time with other companies in a diverse range of industries. He now works as a solution specialist for SSI, helping shipbuilders globally overcome shipbuilding's unique challenges with technology. And the final presenter is Tim Wilson. Tim has a degree in mechanical engineering and has approximately 20 years of experience, mostly in the automotive engineering industry. He's worked in consultancies and for OEMs, such as Jaguar Land Rover in the UK and Ford Australia. The roles varied from manufacturing quality to simulation, and more recently focused on NVH, noise, vibration, and harshness. Now he's a technical specialist at Altair in Melbourne, supporting their customers with their simulation software and processes. I'm going to hand over to Angus now to start. We have to pass the microphone between people, so please just bear with us.
That's great. Thanks for your introduction, Tom. Welcome to this evening's talk, which is on CAD CAE Workflow, looking at the capturing, validating, and optimizing of foundation structural design in shipbuilding. So this presentation is a specific part of the ship design process, which is used for every new building and every repair project. Adding equipment or machinery to the ship is carried out by designing a foundation or seat, which is sometimes referred to as, which provides the interface between the primary hull structure and the equipment and machinery. We've used this example because it's well understood by naval architects, and it's also something where the universal value in making more efficient, both in terms of the process and workflow, and also the quality of the technical solution. The bigger picture as well is that the consideration of the entire design workflow and the utilization of both CAD models and the CAE process to work in an integrated manner, both in terms of, and the loop is closed with the utilization of the PLM system. For this example, we use specific software, which happens to work well together, but this process applies agnostic of the CAD, CAE, and PLL systems which are used by any organization. Both Altair and SSI have open architecture philosophy, which also makes implementation of this more practical. So the scope of foundation design. Basically, we're taking the raw materials and the equipment, processing the data, and producing the technical solution. This is done by taking a ship specification, a building and repair contract, and working that against a set of rules or standards to develop the design. And then the design concept is refined through the calculation process. The design of foundations ranges from the large CAD items, which are the propulsion and main items of equipment which are integrated into the ship structure, through the intermediate or CAD-B items, which are the significant heavy items of equipment, down through the CAD-Cs, which are the smaller items. So in a complex new build design, there may be 30 or 40 CAD-As, a few thousand CAD-Bs, and several thousand CAD-Cs. This presentation is focused on the CAD-Bs, which is where the majority of design hours go, but the workflow applies to the CAD-As as well, and also into coming up with a process or design rules for the CAD-Cs. So historical or traditional calculation methods is where you take a two-dimensional drawing and the engineer interprets the load path for different load cases which apply to the vessel. These load cases consist of the magnitude and direction of the forces which act on that equipment and structure. The structural calculations then visit the stresses, deflections, and stiffness to test whether they're suitable, and if not, the design's revised. And if the design passes, then a refining process can take place. So these are traditionally referred to as hand calculations, and they're usually used with a MathCAD or Excel spreadsheet-based platform, or alternatively, a traditional FE process can be used. So just a quick word on data. We treat all our customers' data in the strictest of confidence. And the example that you're going to see delivered later today is a dummy generic style example. When we work up a design workflow, it's always customized to individual organizations, their products, priorities, tools, and people. This presentation follows is suitable to all sectors of the industry, from naval shipbuilding, oil and gas, commercial shipping, renewables, and mega yachts. So seat design has formed a significant portion of my particularly early career, and the pictures at the bottom here show some of the projects that I've been involved in and give a flavour of how foundation design sits within the design process. So running from left to right, the first is a Type 45 destroyer, where I worked on the FE for the CAT-A seats, including the main engine and gearbox seats, and through a range of the typical seats, which would be pumps, transformers, racks, strainers, these sort of items of equipment, and then some interesting things like the breakwater up forward. The next is a picture of a reefer ship where I was involved in long-term through-life support for the management company. So the foundation aspect that's involved there is twofold. There's the operational constraints where you look at the loading conditions and improving or increasing the capacity, and then also meeting legislative requirements where additional factors need to be brought into the design through life. So for this vessel, for example, there was shore power was brought in and exhaust gas scrubbers were added as well. The middle one's the odd one out. I didn't design part of that. That's not a yacht Rasha, but I was the owner's representative. So the owner of the reefer fleet bought himself a yacht, and it's mentioned there because something is small. It's a 54-meter yacht, but the challenges in the seat design there are just as much as any of the other ships because the engine space is so congested, and the challenges are different, but they're certainly just as real. The next one is the Enquest Producer, which is a FPSO conversion, where the vessel, despite the enormous budget, was brought into dock with no formal specification. So the design house, which was engaged with the shipyard, started off with the big items, the topside items, and they were well progressed through installing those. And then mid that process, they needed to add all the traditional seats, so anything up to 5 tons. There's no calculations, no designs done for those. And that, I'll touch on this later, but that really was a great example of where the designers that do the original design, the original CAD, are absolutely key to the design process. So, you know, I was able on my own to do the calculations for about 160 foundations over the course of a year, which clearly is only possible if you've got excellent designs to start with. And then finally, as Tom mentioned, Alex and I both worked on Queen Elizabeth class carriers, and Altair was involved right from the very bottom and the double bottom. There was optimization work there through the aircraft lift integration and addition of a flyco on one of the islands. And those were 3 technical challenges that we couldn't solve through traditional methods. And Altair came in as consultants to do that, and also some through build construction support as well. So looking at two offshoots is collaboration and alternative methods. So the collaboration between the designers who, as I say, produce the first pass design, and they're typically very experienced, and it's really important that they get the first pass design right for the workflow to work effectively, because typically the more experienced and principal engineers are not involved in the CAT B seats. So it's left to junior engineers and consultants, quite often from other industries. So therefore, the original design from the CAD teams is absolutely critical. Incidentally, on the first example of those, the Type 45, I actually worked with a team of GKN engineers that were based from Melbourne, and they were aerospace engineers that came over to the UK to work for a year on the UK destroyer. So that kind of gives you an idea of sort of cross-pollination of engineers that work. Very good structural engineers, but clearly needed a good basis of design to start from. So the example that we're giving today is a traditional FEA, which uses, in this case, Altair HyperWorks with the UltraStruct solver. It's worth mentioning at this stage, though, there's alternative meshless codes for structural analysis. So these work very differently. And the practical difference is that the basis is using the solid geometry direct from the CAD, and the workflow is considerably quicker, and there's less of the technical expertise needed to use traditional FEA. And although it's a faster and simplified method, the results are incredibly close to traditional FEA. Okay, so my final slide is we're going to demonstrate that we've improved the workflow, or there's a number of benefits to using this. And the first one is that you improve the design process by reducing error of creating or making assumptions for the model data, because it's just imported directly through the process. This increased speed of automating workflow applies both to the model build, but also to some of the automated reporting that we can do, especially for projects where there's consistent design reports required. So where projects are behind schedule, this just directly correlates to being able to save time and catch up on schedule. Where projects are on time, it does allow the engineers to spend more time on refinement and optimization. So the designers are focused on doing the most detailed first pass of the CAD with this process, and the engineers can investigate the optimization of the design in different ways, and also look at novel solutions. For example, this chalk is an additive manufactured item. And the final point to note is, in an ideal world, you do the design and it gets built, and that's the end of the story. But shipbuilding is definitely not an ideal world. So rework varies from, I think the best I've probably seen would be about 20%, and I've seen well over 100% for long-running new build projects. Using the process that we're going to show just now, the reruns for models that have been created are very, very much quicker. So your efficiencies compound over the length of the project. I'll now pass over to Simon, and the technical part will begin.
Cool. Thank you, Angus. Before we get to the validating and optimization of the structural design, I'll be talking about the change management associated with doing that task, starting with finding the information we need, capturing the 3D geometry and metadata, and then executing the change. Firstly, a bit about SSI. So SSI is a Canadian-based company founded in 1990. We've been a part of the business of shipbuilding for over 30 years. We're a bit unique in this space as a privately held company that only focuses on shipbuilding, nothing else. We create technology for shipbuilding, and our people, salespeople, and our services team have all been working as, with, or for shipbuilders for a very long time. Here's a small sample of some of SSI's 440 plus clients globally. There's over 7,000 users, and designers of using the software work on every type of vessel. In Australia, the biggest clients include Austal and BAE. To overcome the challenges facing shipbuilders, we believe in a single source of truth for manufacturing information. The platform must be tightly integrated with engineering and must effectively track and manage constant change. SSI has built a vendor-agnostic open shipbuilding platform consisting of Ship Constructor, Shipbuilding PLM, and Information Hub. In combination, they provide a platform which will act as a source of truth for manufacturing information, connecting to other platforms used in the shipyard. To be successful, the platform needs to be a tightly integrated combination of CAD and PLM, and are both designed for the business of shipbuilding. The entire platform needs to be based on open, accessible technology that can be seamlessly connected to other platforms, processes, and tools. This includes specialist analysis software like Altair HyperWorks. Performing FEA throughout the ship design process is certainly not a new workflow. Models are often created specifically for each use case with the level of detail suitable to perform the analysis. Aside from double handling work, there's a risk of user error. NSRP, or National Shipbuilding Research Project, is a US government-funded program that works with shipyards and industry partners to overcome some of shipbuilding's unique challenges. One of the programs, LiftShip, was created to leverage existing FEA workflows at shipyards as the basis for automating large-scale lifting, turning, preparation, analysis, and reporting. Some of these include some of US's largest naval shipbuilders, Huntington Ingalls, Fincantieri Marinette Marine, and VT Halter. The same workflows we'll see today on a smaller scale foundation. So before we get to the good stuff, the validation optimization shown in orange, I'll touch on the rest of the associated life cycle. The software shown today includes Ship Constructor, Altair HyperWorks, and Shipbuilding PLM, although the process would be the same regardless of what software tools are being used. Firstly, we need to find the relevant information. In the example today, calculations are required for all equipment items weighing over 200 kilos. In an ideal situation, within the common product model, a user-defined attribute would exist, telling us which equipment items need a calculation and if a calculation has been performed. It's not always the case, but the PLM system or master equipment list can be searched and that information can be found. Then we need to capture and reuse the information from the common product model. For a transformer, this includes the transformer itself, the nominal foundation that the designers put in, the surrounding structure and associated metadata such as material, grade, thickness. Then the foundation's analysed and optimised using specialist software. Once the assessment's complete, the change needs to be made. Depending on the design maturity and internal processes, this usually results in the creation of an ECO or engineering change order, where design changes are assigned and tracked. Finally, the changes need to be executed and tracked before being approved, rejected, or changes requested. I'm trying to see play on it. Now we'll take a look at the process, finding the information. Shown here in shipbuilding PLM, search for the equipment items in the model weighing 200 kilos. Aside from the propulsion system and power generation, transformers are some of the heaviest items on the ship. Against the part, we can see properties such as weight, the compartment, and centre of gravity. We can view the associated parts and drawings, a 3D viewable of the equipment. We can view the requirements that led to fitting the transformer and view VFI documentation from the supplier. Next up, capturing the information and reusing it. The sample vessel shown here is an 80-metre anchor handling tug. The transformer has been placed on a nominal foundation placed by the designer. This forms the basis of the analysis. The transformer foundation and surrounding structure need to be included. Filtering for the parts, assemblies, or structural sections, we'll find that information and select an operation to create a step file of each part and an XML containing the associated metadata, material, grade, thickness. For this example, it takes less than 5 minutes from a desktop machine to generate the information required to do the analysis. From a technical point of view, a step file is created of each individual part and an XML list of all the parts containing the part properties extracted from the common product model. Parts can be selected one by one, or in this case, the easiest way to capture the information is to select the structural sections contained within the area of interest. The XML file contains material, grade, and thickness. Following the design validation and optimization, back in shipbuilding PLM, an engineering change order is created. This depends on the maturity of the design and if there's a requirement to track the changes made to the model. When creating the change, all affected equipment is identified, and supporting documentation like the report from Altair, PDFs, and model geometry can be attached to this entry. Following the creation of the ECO, a ship constructor task is created. On the left is the example of the task assigned to each unit, updating the model and then updating the production drawings. Designers complete the work assigned to them under each task. Tasks track the model and drawing changes down to the part level. Finally, the changes will be approved, rejected, or rework requested. Here's a technical look at that workflow we just saw. Engineering change order is created to execute the change. The design report and the relevant model geometry is attached to the ECO for designers to reference. Designers execute the changes and all changes are managed and tracked under that ECO. This includes my part of the presentation. And for more on SSI, check out the website or the blogs, in particular the solution blog, where my team and I discuss actionable strategies solving shipbuilding's unique challenges. Thank you.
All right, thank you, Simon. So my name's Alex Quirk. I'm the sales manager for Altair in Australia and New Zealand. I'm going to be giving a quick introduction to Altair for those of you that aren't familiar, before my colleague Tim takes you through the technical workflows for this particular example. So Altair was founded in 1985, one of the largest engineering simulation organizations in the world, with offices in 25 countries and over 15,000 customers worldwide. In total, we now offer over 150 software applications in total. And those software applications fall under four main categories of physics simulation and concept design, data analytics and AI, high performance computing, and the Altair Partner Alliance, which is third-party applications available under our own licensing system. And those 15,000 customers include every single one of the world's major automotive and aerospace OEMs, as well as the majority of major shipbuilders and even shipyards around the world. Both commercial, high-performance yachts and defense. Our customers also include some that you may not expect, like Facebook and Qualcomm, and the financial sector with our artificial intelligence technologies. And one thing that's pretty unique to Altair in this region is that we are Altair. You know, a lot of companies in this space don't have a dedicated office here in Australia, but we have a good team based mainly here in Melbourne, but also in Sydney and in Auckland. And our main focus has traditionally been in simulation technology, where we're increasingly focusing on multi-physics and mixed fidelity applications, so that you can make sure you apply the right technology at the right time to be able to capture the true behavior of your asset without having to compromise on what you're simulating and how. And that's augmented by the availability of high performance computing, both in on-premise and in the cloud, which allows you to do much more large-scale design exploration studies with DOEs and optimization and the like. And finally, in the recent years, we've branched out and acquired an organization focused on artificial intelligence. And again, all these new technologies allow us to provide more information earlier on in the design cycle, so that organizations can make better decisions with more information. So this artificial intelligence augments that technology in design exploration and optimization. And one of the key factors, though, is being able to automate this technology, make it seamlessly connect with third-party tools, so that you can very easily move through the design cycles, and you don't need to be an expert in every single aspect to get the outcomes that you need. And Altair has been a leader in marine engineering for many years now, in a number of different areas. So including racing in the America's Cup with SailGP and other organizations, looking at design and optimization of composite structures, topology optimization, and even fluid structure interaction problems for the hydrofoils is a real area of technology development. Also looking at defense, as we mentioned before, Angus and myself have some overlapping experience on carriers and the like. And this is an area of real interest for us because there's some really advanced technologies being put into this, such as advanced shock loading, things that are really important like radiated noise for underwater noise, fatigue, and increasingly even in this space, weight optimization becoming important. The other area we work with is the shipyards themselves. So looking at lifting and turning operations, calculating cable tensions, structural stresses, and process optimization, because you know, a failure in this environment can be very dangerous, but also extremely costly and time-consuming. And there's a ton of auxiliary applications as well. Things like you may not expect, like this collapsible container, which allows you to reduce the space taken by a single container by 75% by an empty container. And also we developed a new LNG tank, which has been patented. It gives all the strength performance of a spherical tank with the volumetric performance of a membrane tank. So there's a lot of almost random aspects that go into marine engineering that you may not expect from us. So just to touch on those three main areas of technology in a little more detail. So starting with simulation. So there's a number of areas of simulation technology that's available through the Altair platform where we work in marine engineering. So starting with stress and noise, which is where we're going to be focusing today. So there's an optimization. So in optimization, there's technology, like Angus mentioned, the flight control module. So we're able to take the original packaging space, run a topology optimization to identify the load paths, and then perform an engineering interpretation of what that might look like, followed by a further optimization of that stiffening structure. And in this case, I think we're able to save about 15–20% of the weight while improving the performance. The other areas include electromagnetics for radar cross-section, modeling radiation hazard, antenna placement, wave propagation, these sorts of applications when installing antennas on the ship. Also for fluid dynamics and thermal analysis, such as HVAC, hydrodynamics, and a couple of thermofluid structure interaction problems. In the naval space, underwater explosions is a key criteria in the performance, obviously. So being able to do this quickly and efficiently is extremely important, and our new boundary element method allows you to do it in a fraction of the time of traditional approaches. And again, more and more the issue of weight is coming up in this area. So being able to predict the performance of different manufacturing methods, such as additive manufacturing and composite materials, is becoming more and more important. And finally, the through-life support for vessels is essential and is actually extremely expensive. So doing this efficiently and accurately by ensuring that you're not wasting time maintaining assets that haven't been loaded, but also making sure, obviously more importantly, that assets don't fail in service is very important as well. So there's the Altair tools, also available under the licensing that we supply a number of third-party tools, including Maestro, which looks at optimization and global ship modeling, Ship Mode 3D, which looks at ship dynamics, and Proteus DS for systems that bolt onto the ships and apply loads such as tow arrays and these crane assets. So I will just touch on the other areas very quickly, such as areas of data analytics and AI. You know, this is, we're showing an F1 example here, but this sort of ability to, in real time, monitor behavior and data can be really useful, as well as being able to look back. So this is really useful for asset monitoring and management. And then in the high performance computing region, where we talk about, you know, this really augments the technology and allows you to run much more than you would otherwise. So we have PBS Pro workflows, which primarily allow job scheduling so that you can run multiple jobs on a given system and be confident that they're going to complete in time. But then a lot of organizations don't have high performance compute systems. So we actually supply physical appliances, a turnkey solution to basically design custom high performance compute systems, which we install on site. Or alternatively, if it's an ad hoc requirement, the cloud is a very good option. So all of our applications are available as a turnkey solution on the cloud as well. So yeah, so just to conclude my section, there really is an end-to-end solution from concept design, detailed design, connectivity and data science, and underpinned by model-based systems engineering technologies and high-performance computing and the cloud. So I will now pass over to Tim to work through the example on today's model.
Oh yeah.
Okay, good evening, everyone. My name is Tim Wilson. I'm from Altair, technical specialist. And we're going to just play this video to just show some of the workflows that we've been talking about and how that would look interactively. Okay, so we're taking the solid geometry from Ship Constructor, from the CAD and PLM system, and obviously trying to not just capture the geometric data, but the non-geometric data as well that has the properties, the materials, the gauges, and so on into the model. Then we're creating a mid-surface representation of that. We're removing some of the features which are not necessary. So we're focusing on the detail of the foundation on this part, and the surrounding structure we can represent as a more simplified part. So we remove the features we don't need, maintain the ones that we need to keep, and obviously get an accurate solution from. So here we're just removing some of the cutouts on this model. And then we're going to focus on the design of the foundation here, which supports the transformer on the vessel. So you can see the mid-surface has been created, but the surface is not yet stitched together. So we just need to reconnect those mid-plane representations of the geometry, so we can produce a shell mesh of the model. So we can produce a much more efficient FE model of the structure by using a shell mesh rather than a fully solid model of the structure. So we can modify the geometry. I mean, ideally, the CAD and the designers have given you the model, the details you need, but you can also modify it in HyperWorks, as seen here, if you need to. So if you need to add features that are missing, or maybe add features to change the design and see how that affects the results when you validate the parts or when you're looking to optimize the parts here. So here I'm just showing you can quickly sort of copy and paste some of the ribs from the features of the model, move those to new position and stitch them back in. So if you need to add features and modify the design, as I said, you can do that fairly easily in the new version of the software with the modern interface we have now. So the roof's been copied and offset. And then it just needs to be stitched back into the main structure here. So we're just imprinting the new surfaces we've duplicated to support the structure there, imprinting and connecting into the rest of the surfaces there. So if the design has all been completed in the CAD, you obviously don't need to do this step, but these are extra steps you can do if you need to go further and make any modifications for the simulations. So color coding on the screen, you may not be able to see it clearly, but the color coding shows the different color lines as to whether things are connected properly and things, so you can quite quickly and easily see if your model's of good quality and if you need to repair or fix anything. So top left is the key there with the red, green lines and so on. Once you're happy with the geometry representation of the mid surfaces and they're all connected, you can just perform the meshing on the parts. So there's a number of different methods to do the meshing. You can do it like a one-step mesh with a constant element size, or you can have a refined mesh in the areas of interest, and then of course a mesh around the outside to reduce your model size. This example is obviously not the biggest model, but some of the models are much larger, and you need to focus more on not making sure the model is not too large. So you can see the thickness is now visualized on the shell mesh here. The thickness data has come from Ship Constructor or your CAD system. So as much as, so the idea is to import as much of the data from your CAD and PLM system and make sure that's automatically assigned to reduce any errors and to speed up the process. Then the properties and materials. So the properties get brought in automatically and you just need to check the materials are assigned and everything's looking correct for the model. So just do your final quality checks on the model. So you can review in the browsers all of the geometric information and the non-geometric information, such as your thicknesses, materials, etc. Okay, so now just zooming in on the foundation design. So it's a generic foundation. So the process that we push with Altair is to don't spend too much time up front with a design. If you work with a sort of a generic and more heavy design, you can let the optimization tools tell you what the most efficient layout is for the material and the gauges and so on. So here we're just putting in some connections for a simplified representation of the transformer in this case. Obviously you can add more detail if you need to for modeling the bolts and things, but just to show an example, here we're just having a concentrated mass to represent the transformer mass and center of gravity. And then we're going to create and apply some boundary conditions, gravity loading, so acceleration in different directions, and then also do a modal analysis for the structure. So there you can just see the transformer in wireframe and just a concentrated mass added to represent the center of gravity, mass and inertia for what's mounted on the foundation. So we need to add the boundary conditions. So this is just a segment of the structure of the ship. In real life, this will be attached obviously to the rest of the vessel. So all the boundary areas where it will be connected into the main ship, we need to apply the boundary conditions in the relevant directions and support the structure in the XYZ or rotations as necessary to support this design for the simulation. Then we create a few loads here, so gravity loads, so we can assign gravity and put in some 2G, 3G loads or whatever is specified for the vessel, looking in the XYZ directions, and then create the load steps that link up which boundary conditions we're applying at the same time as which loads. So a lot of it's just done from the model browser on the side. You can right click and create most of your entities in there and link up the load cases and the settings you need to analyze the structure. And then you run it in your solver. So in this case, we're using OptiStruct. We're reviewing the stress of the structure. In this case, looking at, I think this one's the vertical G loading, 3G loading, and then the other windows here, you can see we're looking at the gravity loading in the different directions and different magnitudes. So you can create reports from HyperWorks as well. So you can have multiple windows and pages, and then export these to PowerPoint or Word, and gather what you see is what you get type of report. And then we can go on to the optimization. Once we looked at the validation of the stress, we can optimize the gauge here. So you can see the colors changing as it's optimizing to reduce the gauge to meet your stress, stiffness, and structural targets. So you're maintaining those targets, but making it as light as possible. And then you can go on to doing topology optimization, which is actually where we're looking at actually removing some material from the structure here and looking at the most efficient load paths and the structures, again, to meet our criteria. So the initial design is sort of too heavy on purpose. So we can reduce the gauges, look at the best load paths with topology, revise the design based on these directions, and reduce the weight of the parts. So here you can see for the gauge, the topology analysis, it's gone from about 14 to about 4 kilograms in that example. Obviously, the first design is not one that's been, optimized fully, but it illustrates how you can quite easily take out a fair bit of weight from the designs. Even if the design was tailored a bit more carefully, there's still, scope for good changes of good improvements of weight of 20 to 30% or more potentially. So that's a very quick overview of the process of how it looks interactively in HyperWorks, taking the data from Ship Constructor and going through the simulation process to validate and optimize the foundations in the vessels.